All right, new section, section 3.2 and 3.3. So in these sections, which I'm going to kind of lump together, we're going to learn something called the fundamental theorem of calculus. So if that sounds pretty important, good, because it is. And we're also going to get into the idea of antiderivatives, which is kind of interesting, right? We spent the last, couple months learning what most people call calculus 1, where we learned how to take derivatives. And in this section, we're going to take antiderivatives, kind of the opposite of derivatives, loosely speaking. And it'll turn out that these two concepts are closely aligned, and perhaps surprisingly, they're going to help us find a better way to do this. And I mean, just by looking at it, there's got to be a better way. This is what I call some bonus material, where we learned how to find the actual area underneath the curve, and we did it by evaluating this limit, by calculating the area of infinitely many infinitely thin rectangles, which is kind of wild. It was super duper hard, and I made it bonus for a reason. It'll turn out there's a different, better, I guess, way to answer this exact same question. And to understand that, perhaps surprisingly, you have to understand antiderivatives. So first things first, let's talk about antiderivatives. In the last section, we spent a ton of time trying to figure out derivatives, right? So a typical question from chapter 2 might ask you to take the derivative of this expression here. We first learned how to do this by evaluating the limit of the difference quotient. So I know it's been a while, but at some point you were able to figure out the limit as h approaches 0 of maybe f of x plus h minus f of x divided by h, where f of x is this expression, x cubed minus 6x squared plus 10x plus 2. But then we learned that there's a different, better, I suppose, way to figure it out by using these different polynomial rules. We said the derivative of a sum or difference is just the sum or difference of the derivatives, so we can just take the derivative of each of these terms individually. We pulled coefficients out in front, we applied the power rule, and what you're able to figure out is that this derivative is 3x squared minus 12x plus 10. We did a lot more than this, right? This was kind of the basic derivative rules to get from here to here. We also learned product rule and quotient rule and chain rule, etc. But I don't know, when you're looking back on this class in 10 years or something, if you're trying to think about what you did in the first half of business calculus, you might think of an example like this as kind of your standard question. We figured out a whole lot of derivatives. In chapter 3, what we're going to do is reverse this process. Instead of giving you x cubed minus 6x squared plus 10x plus 2 and asking for 3x squared minus 12x plus 10, I'm going to ask you to go backwards. So I'll give you something like, x cubed minus 6x squared plus 10x plus 2, but I won't want you to take the derivative. I'll want you to figure out what function we must start out with for someone to take the derivative of that function and get that as their answer. This is no longer the question. This is the answer, kind of loosely speaking. It might not surprise you to hear that we're not going to write things this way with the kind of question marks. The way we're instead going to write things is like this, which might look kind of familiar, right? You saw this sign in the previous section when we were talking about definite integrals, except there was a number here and a number here. Weird, they look kind of similar, but for now, there's no connections between the previous section and this section. This is just new notation, and this is asking you to figure out the function so that when you take the derivative of that function, you get this as your answer. So you're kind of thinking backwards. It might feel something like a puzzle. And it's actually kind of a fun puzzle. I mean, you might want to pause the video and see if you can come up with a function so that when you take the derivative of that function, you get x cubed minus 6x squared plus 10x plus 2. If I were doing it, what I would probably do is think about, well, let's see, how do I take derivatives? When I'm taking derivatives of polynomials, what I do is I subtract 1 from the exponent and bring it down in front. So if there is something that I took the derivative of and I ended up with an x cubed, I must have started with an x to the 4th power, right? Because I have to subtract 1 from this exponent and get this x cubed. But I couldn't have just started with x to the 4th, because if I started with x to the 4th and I took the derivative, I'd get 4x cubed. But I didn't get 4x cubed, I got x cubed. So what happened to the 4? Well, maybe there was a constant out in front, right? Maybe there was some number here so that when I brought the 4 down in front, it interacted with that 4 in such a way to leave me with a 1 as the coefficient. What would that number have been? Well, it would have had to have been 1/4. Because look, if you take the derivative of 1/4 x to the 4th, the 4 comes down in front, 1/4 times 4 is just 1, and then I get x to the 3rd power, which is exactly what I end up here, 1x to the 3rd power. I can kind of do that same logic here, right? I must have had x to the 3rd power to end up with x to the 2nd power, but now I have to kind of adjust the coefficients. If I took the derivative of x to the 3rd power, it would have brought the 3 in front, and I'd get 3x squared. But I don't have 3x squared up here, I have negative 6x squared. So there must have been some number out here so that when I multiply it by this 3, I end up with negative 6 as the coefficient. That number must have been negative 2. It's starting to make sense? See if you can do it with this next term. Let's see, I have x to the 1 power. So in order to end up with x to the 1 power, I must have had x to the 2 power. But be careful, I didn't have exactly x to the 2 power, because if you take the derivative of x squared, the 2 comes down in front, and you subtract 1 from the exponent to get 2x. We didn't get 2x, we got 10x. So there must have been a 5 out in front. I got 5x squared. Finally, this 2, what could I have taken the derivative of to leave me with a 2? Well, how about 2x? The derivative of 2x is just equal to 2. If I took the derivative of this function, I'd get this function, so this is my answer. Kind of. This isn't the only possible correct answer, and that might kind of surprise you. There's actually infinitely many functions out there, so that when I take the derivative of that function, I end up with this. Wait, how can there be infinitely many? Think about constants. When we take the derivative of a constant, we end up with 0. So there might be a, I don't know, like plus 7 right here. When I take the derivative of this function, I'd still end up with this function. Because when I take the derivative of this constant, it just goes away. So it could have been a 7, or it could have been a, I don't know, minus 4, or there could have been nothing here at all. So that's kind of a challenge when we're working backwards, is that we could always have extra constants here. Because the derivative of constants are just 0, there might be a constant here in this function that we're taking the derivative of to produce this function. Often people just leave off the constant, but really what you should do at the end of each of these answers is tack on a plus c. This just indicates that the function that when I take the derivative of it, I get this is the answer, could have any constant out at the end. C just represents any constant. If you're asked this question, this would be your answer. If you're like most students, that's a little bit challenging. It feels more like a puzzle. You were finally comfortable with some derivatives, and now we have to think about everything backwards. It's so easy to mess something up. Well, I got good news for you. Antiderivatives are kind of challenging to come up with, but they're really easy to check. If I take the derivative of this antiderivative, I better get this as my answer. Let's see if I do. What's the derivative of 1/4 x to the 4th minus 2x cubed plus 5x squared plus 2x plus some constant c? Well, this is just a polynomial, so it's easy enough to take the derivative of. I take the derivative of each term individually. For this first term, I leave the 1/4 alone, and then I multiply that by the derivative of x to the 4th power, which is 4x cubed. For this next term, I leave the negative 2 alone, and then I multiply that by the derivative of x cubed, which is 3x squared. For this next term, I leave the 5 alone, and then I multiply that by the derivative of x squared, which is 2x. For this next term, I leave the 2 alone, and I multiply that by the derivative of x, which is just 1. And then finally, I take the derivative of c, which might be a little bit confusing, but remember, c just represents a constant. And when I take the derivative of a constant, I get 0. The derivative of this polynomial is this expression, and if I clean things up a little bit, 1/4 times 4x cubed is just x cubed. Negative 2 times 3x squared is negative 6x squared. 5 times 2x is 10x, and 2 times 1 is just 2. Sure enough, what I get here is exactly what I started out with right here. If you have a hard time going from here to here, no worries. Just try your best, come up with this answer, and know that you can always check it by going back from here up to here. Although I think what you'll see is eventually, as we get more practice calculating antiderivatives, you won't need to check all these answers, but you always have that option. If we were in a classroom right now, I'd kind of check in and see how confused everybody looked and see if it seemed like you were able to come up with this antiderivative from this function. And if so, that's great. You're picking up everything just the way you should. But if you couldn't, we might drill down and try to figure out what was going on. And you might be like, well, I really like taking derivatives because I had all these different rules. I knew exactly how derivatives worked. I know that the derivative of a sum or difference is just the sum or difference of the derivatives. I know that I can pull constants out in front and take the derivative of powers like x to the 4th or x to the 3rd or x to the 2nd using the power rule. I had all these rules that we laid out for derivatives. Can you give me some rules for antiderivatives? And the short answer is absolutely. And the good news is they're very similar to the rules that we had for derivatives. The first rule that we learned for derivatives, if I kind of use some shorthand here, is that if you have the sum of two different functions and you're taking the derivative of that thing, all you have to do is take the derivative of the first thing and then add on the derivative of the second thing. It turns out that something very similar holds for antiderivatives. If you're taking the antiderivative of a sum of two different functions, all you have to do is take the antiderivative of the first function and then add to that the antiderivative of the second function. The next rule we learn for derivatives is sometimes you'll have a constant times a function that you're trying to take the derivative of. And when you're in that case, you can completely leave the constant alone. You can pull it out in front and then just multiply that by the derivative of the function. Turns out something very similar holds for integrals. Sometimes you'll be taking the antiderivative of a constant times a function. And when you're in that case, you can completely ignore the constant and just multiply that by whatever you get when you take the antiderivative of the function. The next derivative rule that we learned was a really powerful one. It was called the power rule. That wasn't meant to be a pun. And what it said is if you have your variable raised up to some power and you're taking the derivative of that thing, what you do is you bring that power down in front and then you multiply that by the variable raised up to 1 less than the old power. Well, it turns out there's a rule very similar to this for antiderivatives. When you're taking the antiderivative, which I may have called an integral earlier, it'll turn out that those terms are interchangeable. But for now, I'm going to continue to refer to these as antiderivatives. When you're taking the antiderivative of x raised up to some power, where x is your variable, what you do is, instead of subtracting 1 from the exponent, you add 1 to the exponent. And then instead of taking the old exponent and bringing it down in front, you take the new exponent and you bring its reciprocal down in front. That's kind of weird. Nah, it actually makes more sense than you'd think. Just think about taking the derivative of this side of the equation. You bring the n plus 1 down in front, that would cancel out with this 1 over n plus 1. You'd subtract 1 from n plus 1 to get n. You'd be left with just x to the n power, what we see over here. It's often challenging to go in this direction. This is the new thing. It's a lot easier to work backwards in this direction. Technically, the antiderivative of x to the n power isn't just 1 over n plus 1 times x to the n plus 1. That's an antiderivative of this function. It's not the antiderivative of this function. In order to have the antiderivative of this function, I have to keep things as general as possible. And I should make the comment that we can always tack on a constant, a plus c here. But if you want to leave that off for now and just remember this part of the power rule for antiderivatives, that's totally fine. We learned a lot more derivative rules, but there's two in particular that I want to focus on. We had to take the derivative of e raised up to the x power, and when we did, this was a really nice one. The derivative of e to the x was just e to the x. We also sometimes ran into natural logs, and when we had to take the derivative of natural log, what we got for our answer was just 1 over x. We learned more general rules than these. We learned any base to the x power and the log any base of x, but these two will be especially useful for antiderivatives. In fact, I'm going to write the corresponding rules for antiderivatives over here. If the derivative of e to the x is just e to the x, then the antiderivative of e to the x, where my variable is the x, is equal to, well, e to the x. And I guess technically I should tack on this plus c. The derivative of e to the x is e to the x. The antiderivative of this e to the x is this e to the x. And finally, one that confuses a lot of students is this last one. If you're taking the antiderivative of 1 over x, it's tempting to look at this and think, oh, this is x to the negative 1 power. It's tempting to try to use this rule, but you can't. Because if you think about this as x to the negative 1 power, then n is negative 1. If n is negative 1, n plus 1 is 0. So I'd have 1 divided by 0. I'd come up with something that's undefined. I can't use this power rule for 1 over x. It works for any other exponent, just not negative 1. So what do I do in this case? Well, I think about this example. If the derivative of natural log of x was equal to 1 over x, then the antiderivative of 1 over x must be equal to the natural log of x. Technically, I should tack on a constant.
One more minor comment. 1 over x is defined for any value of x other than 0, but natural log of x is only defined when x is a positive number. So in order to make the domains match up nicely, we throw the absolute value symbols around the x in natural log of x when we're taking antiderivatives. I just forgot to write them in this video.
Eventually, we're going to come up with a whole host of antiderivative rules, but the first little group of antiderivative rules are what you have written in red here. And I call them the polynomial rules, even though that's a bit of a misnomer. Really, it's only these first 3 that kind of deal with polynomials. But most books, yours included, tosses on these next 2 in this section, and I don't really have a great name for these and these, so I call them the polynomial rules, even though there's a little bit more than just polynomial rules. With these rules, maybe you can see if you can take these different antiderivatives. That's the last thing we're going to do in this video. There's 5 questions, a whole bunch of antiderivatives. See if you can figure them out. And hint, just like when we were first learning derivatives and you wrote things in maybe more steps than you currently do. At this point in the class, you could probably look at this and immediately jump down to this answer. But when we first learned it, we wrote intermediate steps like you see here. You might want to write some intermediate steps here to really justify your process. That's what I'm going to do as I work through these different problems. First one, antiderivative of 5x cubed minus 3x to the fourth plus 4x plus 5. It's a lot like the example that we used up here, but since it's so important to be able to figure out antiderivatives for polynomials, I want to work this one out even though we've already done something similar. A good way to think about this is I'm taking the antiderivative of a sum or difference of a bunch of terms. So really what I want to do is take the antiderivative of each term individually. I got the antiderivative of 5x cubed, and then to that I want to add the antiderivative of negative 3x squared, and then to that I want to add the antiderivative of 4x, and then to that I want to add the antiderivative of 5. You might notice that in each of these cases I've written a dx here. You can completely ignore this dx for now. For now, this symbol and this symbol is just telling you they kind of work in conjunction, that you want to take the antiderivative of what's in between here. Really, it'll turn out that this symbol kind of specifies what your variable is. And when you're in a class that has more than one variable, we don't, but when you're in such a class, it'll be really useful to know what variable you're taking the antiderivative of. But for now, you can ignore that. Think about this and this as kind of bookends, and the stuff in between it is what you need to take the antiderivative of. So I've taken this one question and I've broken it up into 4 different questions. This first question, I got the antiderivative of 5 times x cubed. It's a constant times x cubed. When I'm taking the antiderivative of a constant times x cubed, I can pull the constant out in front of the antiderivative symbol. So I got 5 times the antiderivative of x cubed. Same thing on this next one. I can pull the negative 3 out in front, and I got negative 3 times the antiderivative of x squared. Similarly here, if I pulled the 4 out in front, I'd get 4 times the antiderivative of x. And then finally, if you really want to pull stuff out in front, you could, you don't have to, pull this 5 out in front of this symbol, and I would have the antiderivative of 1 if I pulled a 5 out in front. Before I go another step, I think I want to add one more rule on here. I don't know that we really need it, but when we were taking derivatives, I also made the point that the derivative of your variable x is just equal to 1. And you don't really need this rule. You can almost get there from the power rule, but it's not a bad idea to write it just to remind students what's going on here. Same thing over here. If you're taking the antiderivative of the number 1, well, what you end up with is just x. Or I suppose if I want to be as complete as possible, I should say x plus any constant. The derivative of x plus any constant is 1. Therefore, the antiderivative of 1 is just x plus whatever constant I want. I now have all the tools that I need to tackle another line of this antiderivative. I got this 5 that's not in between my antiderivative symbols, so I'm not taking the antiderivative of it. What is in between these symbols is x cubed. X cubed fits this rule, playing the role of the n is the number 3. So its antiderivative is 1 divided by 3 plus 1 times x raised up to the 3 plus 1 power. In other words, 1/4 x to the 4th power. You might argue that really, when I'm using the power rule for antiderivatives, I should tack on a plus c. You could argue that there should be a plus c right here, and I'm going to write it this first time through. But what you'll see is there's a way to get around this. You don't really have to write this. But maybe just for completeness, this first time through, I'm going to write it. Let's move on to this next term. The negative 3 is not in between my antiderivative symbols, so I leave it alone. And I'm going to multiply that by the antiderivative of x squared. Using this rule with an n equal to 2, I get 1/3 x cubed plus c. From this next term, I leave the 4 alone and I take the antiderivative of x to the 1 power. It's again this rule, playing the role of n is a 1. So the antiderivative is 1/2 x squared plus c. And then finally, this last term, I leave the 5 all alone, and the antiderivative of 1, as I just tacked on here, is equal to x plus c. I don't have any more antiderivative symbols, so in a sense, I'm done. Although nobody leaves the answer like this. Why not? Because you can simplify it. This c just denotes any constant. This could be any number that I want. So when I get rid of these parentheses by taking the 5 and distributing it through, you might think that I should write 5c here. But I don't have to, because 5c is just some other constant, and I'm not specifying which constant this is, so it really doesn't matter. Maybe c was the number 10 and 5c is the number 50, but it doesn't matter. This c represents any constant. It can be 10 or it can be 50. Similarly, if I took this -3 and distributed through the parentheses, I'd get -3c here. But I don't have to write -3c. I can just write c because c represents any constant. And there's more. If this c represents any constant, and this c represents any constant, and this c represents any constant, and this c represents any constant, when I add and subtract multiples of them, I just end up with a constant. I don't have to figure out what that constant is because c represents any constant. So I don't have to write all these different c's. What I'm saying is I could make my final answer, and this is what everybody does, 5 times 1/4 x to the 4th, in other words, 5/4 x to the 4th, minus 3 times 1/3, which is just 1 x to the 3rd, plus 4 times 1/2, which is just 2 x squared, plus 5 times x, plus some constant c. You don't have to tack on the plus c's in each of these different terms. What you can do instead is leave all of these out and just remember at the very end to tack on a plus c, because the plus c represents any constant you want. So to be clear, at some point you'll look at this and immediately tell me this final answer. But right now it's probably not a bad idea to show a little bit of work in here, but you don't have to show this plus c every time. So what I would probably recommend you do is maybe jump to this line first and then all the way down here. Although I'll leave it up to you. I think individual people want to show more or less work as they go through here. Let's do a couple more examples. This one that you can barely see is asking us to take the antiderivative of 1 over x cubed. Be careful here. Just like with derivatives, how we couldn't just say the derivative of x cubed is 3x squared, so the derivative of 1 over x cubed should be 1 over 3x squared. We can't do that with antiderivatives either. We can't just take the antiderivative of the thing on the bottom. What we instead need to do is rewrite this into a form that fits our rules. And the way we do that is we'd say we want the antiderivative of x to the -3 power. What's the antiderivative of x to the -3 power? Well, I'm going to use the power rule for antiderivatives. We're playing the role of n is a -3. So I want to add 1 to that -3, which gives me -2 as my new exponent. And then I multiply that by 1 divided by n plus 1. So 1 divided by -2. Not a bad idea to tack on this plus c. You could call this your final answer, although nobody does, because it's just ugly. You can clean this thing up a little bit. Usually you don't leave negative numbers in the denominator of fractions. You instead say I have the negative of 1 over 2. And then usually you don't leave your exponents as negative. You instead say that x to the -2 power is the same as 1 over x squared. So I think most people would write this answer as -1 over 2x squared plus c. Just like we need to rewrite this expression in order to fit our rules, if we're taking the antiderivative 2 times the square root of x, we'd want to rewrite that to have it fit our rules. You might first notice that you have this constant of 2, so we can pull that out in front of the integral symbol, the antiderivative symbol here, and the square root of x is the same as x to the 1/2 power. So I can rewrite this question like this. All I have to do is take the antiderivative of x to the 1/2 power. Leave the 2 alone. Playing the role of n in my power rule here is 1/2. So I add 1 to 1/2, which gives me 3/2, and then I multiply that by 1 over 3/2. Rather than having a 1 divided by 3/2 and get fractions inside fractions, it might be easier to just write 2/3, because 1 over 3/2 is 2/3. Either way is totally fine. Don't forget to tack on your plus c, and then it's not a bad idea to simplify this a little bit. 2 times 2/3 times x to the 3/2 can be rewritten as 4 times x to the 3/2 power divided by 3 plus c. If you really wanted, you could rewrite x to the 3/2 power as the square root of x cubed, but I probably wouldn't bother. I think this is perfectly sufficient. I'd leave my answer like this. Hopefully I've made enough room that I can tackle this problem. This problem's kind of tricky. It kind of looks like a polynomial, but 3 of the 4 terms have the x down in the denominator. So I think a good strategy for this is first rewrite this as the antiderivative of 5x to the -3rd power minus 6x to the -2nd power plus 2x to the -1 power plus 1 dx. And then maybe you can break this up into a bunch of different antiderivatives and pull the coefficients out in front to get 5 times the antiderivative of x to the -3rd power minus 6 times the antiderivative of x to the -2 power plus 2 times the antiderivative of x to the -1 power plus the antiderivative of 1. Instead of one big antiderivative problem, I have 4 littler antiderivative problems, and I can figure out each of the individual antiderivatives. For this first one, I'm going to use the power rule. The antiderivative of x to the negative 3 power is x to the negative 2 power, but I got to remember to put the 1 divided by negative 2 out in front. For this next term, I leave the negative 6 alone and take the antiderivative of x to the negative 2 power. The antiderivative of x to the negative 2 power is x to the negative 1 power, but I got to remember to multiply by 1 divided by negative 1. This term is really tricky. It's tempting to look at this term and think that you should use your power rule. But as I mentioned a minute ago, you don't use your power rule here, because if you tried to use your power rule, you'd add 1 to the exponent and you'd get 0, and you'd end up dividing by 0, which is not a good place to be in math. So what are you going to do instead? You're going to recognize that the antiderivative of 1 over x, aka x to the negative 1 power, is just the natural log of x. So I leave the 2 alone, and then the antiderivative of x to the negative 1 is the natural log of x. Finally, the antiderivative of 1 is just x. I remember to tack on the plus c, and I could be done, although, again, it's kind of ugly, right? Maybe it's worth cleaning this up a little bit. I could rewrite this term as negative 5 divided by 2x squared. Make sure you can follow where all the different pieces are going. I could rewrite this term as positive 6 over x. Again, track all the pieces. A negative times a negative is a positive. The 6 is up on the top. The x is down on the bottom here. And then these terms are all just fine the way they look. 2 times the natural log of x plus c. I think that this would be an awesome answer, equivalent to what you see above, but maybe a little bit prettier. One last problem to finish this video with. Good news, it's a fairly easy problem. When you're tackling this problem, recognize that you got a coefficient, so you can pull that 3 out in front, and you're really just taking the antiderivative of e to the x. And the great thing about the antiderivative of e to the x is that it's just e to the x, in much the same way that the derivative of e to the x is just e to the x. So my final answer would be 3 times e to the x power plus c. There's a bunch of different antiderivatives, lots of practice. You might not see how this ties into anything we've talked about so far in this class, but I think as early as the next video, we'll get to see that connection, so it'll be somewhat satisfying. But for now, don't worry about how it ties into anything. If you can take antiderivatives like we did in these examples, you're picking up everything you need.